So this week we're going to focus on reactions, all right, of our aromatic compounds like benzene, okay. We're going to kind of put these into different buckets here. The first one are going to be reactions at what is called the benzylic position. So what do I mean by that? This is going to be the C1 position that's attached to a benzene ring. Okay, so if we have a benzene ring and it has some sort of an alkyl group on there, like for example, what do we have a special name for this one actually? What's this one? Toluene. That carbon, that methyl carbon is in the benzylic position. If we had, for example, propylbenzene, it's got a bigger alkyl group on there. Again, that carbon that's attached to the benzene ring is that benzylic position. All right, so these reactions are reactions that will happen at that benzylic position, the carbon attached to a benzene ring. Okay? For some reactions, we learn a lot about them in terms of like not only these, like what I call the substrate reagent product combinations. Basically, can you draw me the product of this reaction? But we also go and we learn about mechanisms. For these two reactions here that we're going to talk about, all we're going to know is that substrate reagent product combination, right? So what does this reagent do to our particular ring? Okay, our two reagents that we're going to look at, the first one is what's called NBS. All right. Okay, NBS you would have learned about with regards to alkenes. It would have stuck a bromine on the allylic position of an alkene. For this case, it's going to do the same thing, but to that benzylic position. So we're going to call these reactions benzylic brominations. All right, and again, I think that when you're trying to keep track of all of these reactions, having something like NBS, oh, that's benzylic bromination, having that little phrase tied in your mind to that reagent is super helpful. I feel like a lot of students treat it as more information and they're like, my brain can't hold on to that. Your brain will help, it will help your brain hold on to that information by remembering that category of reaction, okay? So, NBS is a shorthand for a larger molecule. To be honest, I probably should, I think I got it. It's something like this. Some big ugly thing like this, all right? And again, it's going to stick that bromine on your molecule in that benzylic position. We don't really draw it out too often. Instead, you'll just see it written as NBS. Okay. And again, what it's going to do is it's going to brominate, stick a bromine, specifically on that benzylic carbon. All right, so in these reactions, we substitute a benzylic hydrogen for a bromine, right? One of those implicit hydrogens on that methyl group, I don't draw it out, is going to be substituted for that bromine atom. All right, let's do the same thing, but now we're going to take our propylbenzene. Again, treat it with that same reagent. All right, based on what we just discussed, see if you can't predict the product here. Again, I'm going to brominate, but specifically that benzylic carbon. All right, so not the ones further down the line, just that benzylic position. All right, and let's do one more here. All right, what if we put a tert butyl group on our benzene ring here? All right, what would our product be? All right, well, my organic chemistry brain is going to explode if somebody puts a bromine right here. What is the problem with this product? I got way too many bonds on that carbon, right? And if you remember, we said specifically that these reactions are substituting benzylic hydrogens for bromine. Well, if there's a tert butyl group right there, my benzylic position doesn't have any hydrogens. So this reaction here would not be able to take place. All right, we would get no reaction. All right, there has to be at least one benzylic hydrogen in order for this reaction to be able to occur. In this particular compound here, there are no benzylic hydrogens. So there's no reaction. All right. Our next reagent here is going to be Na2Cr2O7 sodium dichromate. All right, and you see this a lot with reagents that contain chromium. This is going to be also at the benzylic position, but it's going to be an oxidation reaction. All right, now truthfully, this is a little old school. Nowadays, they really try to avoid these chromium-based reagents because they're terrible for the environment, but a lot of textbooks still have them in there, and you know, we're gonna make our lives easier and just kind of remember the one really common one we see all over the place, sodium dichromate here. Very commonly used in oxidation reactions, okay? So if we take our toluene again, we're going to put in our sodium dichromate. Okay, we also got some other things in our reaction mixture here, specifically dilute sulfuric acid, so H2SO4, and water. Right. What we're going to do is we're going to oxidize. So If you remember back in general chemistry, oxidation numbers was kind of a huge pain in the butt. You calculated oxidation numbers, you had to like memorize a few different rules and stuff like that for assigning oxidation numbers. In organic chemistry, because we're focused on so fewer elements on our periodic table, oxidation and reduction is a much simpler sort of concept. When we oxidize something, we're going to create new carbon-oxygen bonds. Right? And in this reaction here, these oxidation reactions of the benzylic position, you will fully oxidize that benzylic carbon. You will give it as many new carbon-oxygen bonds as it can handle, or create this functional group here, which is what? Carboxylic acid. Okay? And so again, we oxidized this benzylic carbon. We created a whole bunch of new carbon-oxygen bonds, right? Creating that carboxylic acid group. What if we started out instead with propylbenzene? Okay. You will find that if you try to draw a carboxylic acid on that benzylic position again, you will run into a problem where you got just too many bonds. All right, so how do we oxidize this compound here? Well, it turns out that these are really aggressive oxidation reactions, so much so that you will actually cleave off every carbon that comes after that benzylic carbon. So you will again just get that same benzoic acid, and you got something else floating around in solution. We kind of just ignore that. That ethane goes flying off. All right, there is a limitation to this here, and this is if we take that same tert-butylbenzene here. All right, we don't have any sort of a mechanism to better understand why this is, but suffice it to say that there needs to be a hydrogen on that benzylic carbon in order for this reaction to take place. So just like if there was before, if we have no benzylic hydrogen, we have no reaction. All right, so we got two benzylic reactions here, reactions that take place at that benzylic carbon, which is again the one removed from that benzene ring. We can brominate that benzylic carbon using NBS, but we have to have a benzylic hydrogen in order for that reaction to occur. If there's no benzylic hydrogen, we have no reaction. We can also oxidize that benzylic carbon using that sodium dichromate. This will create a carboxylic acid group at that benzylic carbon. This reaction also requires a benzylic hydrogen. So if there's no benzylic hydrogen, again, there's no reaction that occurs. Cool. All right, so those two were kind of randomly stuck at the end of your aromaticity chapter. This will now officially kick off our chapter 16 reactions. These are what are called aromatic substitution reactions. All right, and the one that we're going to spend, like the bucket of reactions that we're going to spend a ton of time talking about over these next two lectures are what are called electrophilic aromatic substitution reactions. right, electrophilic aromatic substitution. We like to get lazy in science, and so you will often hear this referred to as EAS reactions as well. So this is when we're going to take benzene or some benzene derivative, and we're going to react it with an electrophile. We're just going to use E+ right now for generic electrophile. All right, and what we're going to see is we're going to substitute one of the hydrogens on that benzene ring for our new electrophile. All right, so we have these substitution reactions. We talked a little bit last class about how these aromatic compounds do not undergo addition reactions like normal alkenes do, because to do so they would have to break their aromaticity. So these reactions here, notice I didn't change the aromaticity of my benzene ring. It's still nice and aromatic. I just have this other thing substituted on there. All right, so if I'm going to have this electrophile being my electrophile, what role is benzene playing? The nucleophile. All right, so my electrophile, what it means to be an electrophile is not having a lot of electron density, so that's glowing blue, it's cold. And I got my double bond on my benzene ring, my pi bond glowing red hot with its electron density. I guess I gotta use the other one because I picked that hydrogen. All right, and so what we're gonna see is a first step similar to what we've seen before. That nucleophilic pi bond is going to reach out and attack that benzene ring. Okay. Everybody take a second and draw me my intermediate here. All right, so now I have on one of those benzene carbons my hydrogen and my new electrophile that's just formed here. All right, what else am I missing from this intermediate? My charge, yep. So anytime you have a pi bond playing the role of a nucleophile, in this case, this pair of electrons got snatched away from that one carbon to create this new carbon electrophile bond. So it's leaving this carbon up here without that pair of electrons, with an incomplete octet. All right, well now I gotta I gotta get rid of this hydrogen, so now we're gonna have some base. We use generic B with some lone pairs on there. All right, that base is going to deprotonate that ring, leaving me with just that electrophile on there. All right, importantly, I have to reform that pi bond, and that's this pair of electrons that was bound to my hydrogen that's going to do it. All right, so the base removes the hydrogen, and that pair of electrons that was in that carbon-hydrogen bond is now what forms my new pi bond up here, right? This pair of electrons used to be right there. All right, and we're going to learn of a few different electrophiles that we can use in these reactions, but they all have this same basic mechanism here. Your benzene ring is playing the role of a nucleophile and attacking that electrophile. This creates this carbocation intermediate, but this really wants to reform that pi bond so it can be aromatic again. And so some base is going to remove a hydrogen, and that pair of electrons from that carbon-hydrogen bond is going to make up our new pi bond. All right, so again, we're going to learn a few different reactions. They all have this same basic format here. All right, so let's just start looking at these one by one. Oh, whoops. All right, so our first reaction is not going to be a benzylic bromination, but rather just to brominate the benzene ring itself. This will use bromine, all right? And what we're going to see is we always have to include a catalyst. It turns out benzene plays the role of a nucleophile. It's kind of a crap nucleophile. So you need a really good electrophile for these reactions to actually occur. So in all of these mixtures, we're going to see that we have something that's going to convert this electrophile into an even better electrophile, and in this case that's aluminum bromide or iron 3 bromide. Either one works great. All right, so what this is going to do is going to create, it's going to react with that benzene to create what we call our electrophilic species. This is what's actually reacting with that benzene ring. Okay. Both of these, aluminum bromide, iron 3 bromide, kind of the deal is that the metal ion itself accepts pairs of electrons, and so that's what it does. It reacts with this bromine molecule and kind of grabs one of the lone pairs, creating this complex here. All right, let's be good with our lone pairs and our formal charges. When aluminum accepts an extra pair of electrons, it has a minus charge. And when bromine donates that pair of electrons, it has a positive charge. So this is our electrophilic species. This is what the benzene ring is actually reacting with. Okay. And what will happen is it will place one of those bromines on that benzene ring. Not two, don't tell me Br2, that wouldn't make sense in terms of our formal charges. Just one of those bromines end up on that ring, giving us bromobenzene. All right, we can get pretty much the same kind of thing going on, but instead, if we replace bromine with our other halogen, chlorine, and we use aluminum chloride or iron 3 chloride, everybody take a second and tell me what they think this product will be. Just based on analogy of what we just did. Yeah, chlorobenzene. Yep. All right, so these are our two halogenation reactions. You can put a halogen on a benzene ring, either creating bromobenzene or chlorobenzene. our next reaction is what's called a nitration reaction. We take a benzene ring and we mix it with nitric acid. This will put a nitro group on that benzene ring. All right. Real quick, you will often see these nitro groups kind of abbreviated as just NO2. Okay? But importantly, on our homework, you're going to have to draw out the actual Lewis structure. So let's take a look at what that Lewis structure looks like. That nitrogen is double bonded to one of those oxygens, but only single bonded to the other. All right. I got to be good with my formal charges here. When oxygen has 2 bonds and 2 lone pairs, its formal charge is 0. But what if it's only 1 bond and 3 lone pairs? What is its formal charge? -1. Nitrogen likes to have 3 bonds and 1 lone pair. If it's got an extra bond, that means it has a positive formal charge. Okay. Now, like we said, we got to have some catalyst in there that's helping this reaction. And in this case here, you throw in some strong sulfuric acid. Okay, what that strong sulfuric acid does is it dehydrates your nitric acid, creating our electrophilic species for this reaction. Nitrogen dioxide. Nitrogen dioxide has this positive formal charge on that central nitrogen, making it a much better electrophile than nitric acid by itself. Cool. Whoops. All right. Our next reaction is what's called a sulfonation reaction. That's if we take benzene and we treat it with sulfuric acid. Again, this is going to create what's called a sulfonic acid group, SO3H. But again, we want to draw the full Lewis structure here. Sulfur is a weird one. Being a bigger element, it can actually have an expanded octet. And so that's what we see here, is sulfur with these 2, 4, 6 bonds. All right, again, we need to have some sort of a catalyst in here to create an even better electrophile. They call it fuming sulfuric acid. You basically boil the sulfuric acid, and it's the fumes that your benzene will react with. Okay. Again, what happens is that strong sulfuric acid undergoes a dehydration reaction, creating our electrophilic species. Our textbook has this. Another form that you'll see a lot is this or this. I'm going to accept either. Either one's fine. All right. Our last two are kind of special. They have a special name associated with them, and they're one that we want to kind of keep in our brain in a special place because it's one of our few reactions that's going to create a new carbon-carbon bond. Creating new carbon-carbon bonds, those reactions are kind of few and far between, so this is how we could create a new carbon-carbon bond on a benzene ring. These are both fall under this umbrella of what we call Friedel-Crafts reactions. All right, and there's going to be two different ones, what's called a Friedel-Crafts alkylation reaction. This is when you stick an alkyl group on that benzene ring. So let's say that we had chloromethane here. All right, this would then add a methyl group to that benzene ring. This actually uses a familiar catalyst. We've seen it in a previous reaction as well, that aluminum chloride. All right, what the aluminum chloride does is it literally plucks off this chloro group from that methane, leaving us with our carbocation intermediate, so our electrophilic species. For our Friedel-Crafts alkylation reactions, our carbocations. Okay. Because this is an alkyl group, we're going to put a few more examples down because it would really depend on what alkyl halide, alkyl chloride we used. That would tell us what our product is. All right. So let's instead use something like 2-chloropropane. All right, so our electrophilic species is again going to be that carbocation. But which carbon is our carbocation going to form on? Well, again, your chlorine is removed, leaving you with that carbocation. So if I'm going to draw my product here, I need to attach the carbon 2 to my benzene ring. Now, because these go through these carbocation intermediates, we got to be a little careful. Let's do another example. So everybody take a second and give me the electrophilic species of this reaction. right, so again, my chlorine's going to be removed, leaving me with this primary carbocation. All right, but is this thing going to be happy? No, what's going to happen to our electrophilic species here? Yeah, we got to watch out for our shifts whenever we have our carbocation intermediates. And so absolutely what's going to happen is a hydride shift to create that more stable secondary carbocation. All right, so what we'll see here, if we were to do this reaction, we wouldn't get very much of our butyl benzene at all. We would instead get our, I don't know, sec-butyl benzene. All right, where that carbocation shift to that secondary carbocation is then what's going to be attached to our ring here. All right, so just to kind of keep our coloring consistent. Okay, so we have this kind of problem that we got to watch out for any time that we have these carbocation intermediates. That is what's going to happen for these Friedel-Crafts alkylation reactions. So we're just going to make a note here. We got to watch out for those shifts. All right, and the last one is a new type of Friedel-Crafts reaction. I lost my page. Here we go. This is what we call an acylation reaction. Right? This is going to be using, it's very similar. It's just instead of an alkyl halide, your chlorine, your halogen is attached to an carbonyl carbon. All right, and so this, then again, we're going to get that now carbonyl carbon, the carbon that was attached to the chlorine, attached to our benzene ring. I feel like there's 1,000 different names, but this they would call an acyl group here. All right, having that carbonyl group with the carbon bound to our ring, our carbonyl carbon bound to our ring. All right. Our electrophilic species here is also very similar to what we saw before. That aluminum chloride is going to come along and remove that chlorine. All right. This creates another carbocation, but it's a special carbocation. Our carbonyl carbocation all right, and if you thought shifts were a pain in the butt before, then you're in luck because you don't have to worry about them for these. Okay, so it turns out that the carbocation will remain on that carbonyl carbon. It's nice and stabilized by that oxygen, so no shifts. Okay. So just for the sake of practice, let's look. Again, the exact product here is going to depend on what acyl halide I use. All right. So everybody take a second and give me the product of this reaction here. Cool. All right, so now again, we're going to attach at that carbonyl carbon to our benzene ring. All right, so now we have our branch point in there. Okay, so these are our 6 electrophilic aromatic substitution reactions. We're always adding an electrophile to that benzene ring. We have 2 halogenation reactions. We can either add a bromine or a chlorine to the ring. Where am I? All right, so we can create bromobenzene or chlorobenzene. Okay, we have our nitration reaction, which puts a nitro group on that ring, or a sulfonation reaction, which puts a, again, let's just name this. This is a sulfonic acid group on our ring. Okay, okay, hold on. I'm looking at these again. I messed something up here. This one over here has a positive charge. This one over here is neutral. My bad. Yeah, fix those electrophilic species real quick. I messed up my octet rule. Okay, but that'll put that sulfonic acid group on the ring. And then we have those 2 Friedel-Crafts reactions. This is how we can create carbon-carbon bonds, either a Friedel-Crafts alkylation reaction, where we stick an alkyl group on the ring. This one's kind of the biggest pain in the butt because we have a carbocation intermediate. So depending on what alkyl halide we start with, we're going to have to watch out for shifts in that electrophilic species. Okay? Or we can do a Friedel-Crafts acylation reaction. We put an acyl group on that ring. Cool. And so what you should, I'm going to sort of leave it for y'all to do for your homework here. But a great thing to do whenever we encounter a bunch of reactions like this is to take your reagent, your benzene, and make a little wheel with all 6 of those reactions summarized. All right, so I would make this little wheel here where I put benzene in the middle. And I just go around. All right, so this one will be my bromination reaction, or my chlorination reaction, et cetera, et cetera, et cetera. But then you can create this nice little summary of all of those reactions that we studied in one sort of little convenient place. These are also just great study tools to do while you're sort of studying for an exam. Kind of build yourself a little wheel here and then try to fill in as much as you can from memory. All right, just to kind of go around, put all of our different reagents here. Okay, we can use these R groups here for our alkyl groups. All right, that stands for insert any amount of carbons and hydrogens that you like. All right, but these are these 3 reactions that I want you to kind of, I'm sorry, 6 reactions that I want you to create this little wheel for, okay? What we're going to do next class is we're going to talk about these same exact 6 reactions, but we're going to start mixing and matching them. All right, so what happens if I did a bromination reaction and then a nitration reaction? It turns out that you would get a different product than if you did those 2 reversed, if you did a nitration reaction and then a bromination reaction. All right, so we're going to use these same 6 reactions. So having a good site recognition of what each one of them is going to be doing is going to be important. All right, cool.